Welcome to the third pillar of object-oriented programming, polymorphism. This may be the most powerful and often confusing concept, but it is essential for writing flexible, extensible code in any language. The word polymorphism literally means many forms. 1. Definition of polymorphism. In OOP, polymorphism is the ability of an object, variable, or function to take on multiple forms or types. Specifically, it allows a single interface to be used for different underlying data types. This means different objects can respond to the same message or method call in their own, distinct ways. 2. Simple example, the plus operator. The simplest form of polymorphism you've already used is the addition operator, plus. When used with numbers, it performs addition. But when used with strings, it performs concatenation. The plus operator has many forms, and its behavior depends on the type of data it operates on. This is an example of operator overloading, which we maybe will see soon. 3. Types of polymorphism. While polymorphism is a broad term, we will focus on 3 main types within Python. First, DuckTyping, which is Python's dynamic core concept. Second, operator overloading, which we just mentioned. And third, runtime polymorphism, achieved through method overriding and inheritance, which you already have some experience with. 4. Introduction to DuckTyping. Python's flexibility means we don't care about the object's formal class type. We only care about whether it can perform the action we need. The famous saying is, if it walks like a duck and it quacks like a duck, then it must be a duck. This principle is known as DuckTyping, and it is the foundation of polymorphism in Python. To summarize, polymorphism is essential for interchangeable components. DuckTyping means if it has the method I need, I can use it, regardless of its class hierarchy. Join me in Lecture 19.02, DuckTyping. See you there. Welcome back. In Python, the concept of DuckTyping is central to polymorphism. It means that the type or class of an object is less important than the methods it defines. This flexible approach allows you to write generic code that can work with any object, provided that object has the required behavior. 1. The DuckTyping principle. The principle states, if it walks like a duck and it quacks like a duck, then it must be a duck. In programming terms, if an object has the method we are looking for, we treat it as if it belongs to the expected type. We don't need to check its inheritance hierarchy or its formal type. We just check for the method. 2. Defining unrelated classes. Let's define 3 completely unrelated classes: cat, dog, and politician. They do not share a common parent class. However, all 3 classes implement a method with the same name, speak. 3. Creating a generic function. Now we create a generic function, make underscore it underscore spe, that accepts any object we call entity. Inside, it simply calls entity.speak. This function does not care if entity is a cat, a dog, or a politician. It only cares that the object has a speak method. 4. Testing DuckTyping. We create objects of all 3 classes and pass them one by one to the same generic function. Each object executes its own, specialized speak method. This demonstrates polymorphism via DuckTyping. The function treats all 3 objects the same way because they all quack with a speak method, regardless of their actual class type. To summarize, DuckTyping is Python's way of encouraging flexible code design. Our next lecture 19.03, DuckTyping for dependency injection. See you there. Welcome back. We've seen how DuckTyping allows different objects to be used interchangeably. This principle is fundamental to a powerful design technique called dependency injection, often shortened to DI. This technique is used extensively in large frameworks to manage complexity and improve testability. 1. What is dependency injection? Dependency injection is a design pattern where an object receives the other objects it depends on. Instead of creating its own dependencies internally, these dependencies are injected, typically through the constructor or a method parameter. This drastically reduces the coupling between components. 2. Defining interchangeable components. We define two separate classes, email service and SMS service. Critically, both classes implement the same interface method, send. Since they both send a message, DuckTyping considers them interchangeable for any function that needs a send capability. 3. The client class. The notification manager is our client class. Notice that in its constructor, it accepts a service object as a dependency. It doesn't check if that service is an email or SMS object. It simply stores it and later calls service.send. The manager is decoupled. Its logic never changes, regardless of the dependency type. 4. Swapping dependencies. This is where the power of DuckTyping shines. We create an email_manager, injecting the email service. The message is sent via email. Then, we create an SMS_manager, injecting the SMS service. The exact same notify_user method is called, but the output changes because the underlying dependency was swapped. The core notification manager code remains untouched. Only the injected dependency changed. To summarize, dependency injection powered by DuckTyping is key to creating modular, testable, and highly flexible applications. Our next lecture 19.04, Operator Overloading. See you there. Welcome back. Until now, we have used operators like plus or minus with built-in types like integers and strings. But in Python, you can extend this functionality to your own custom objects. This process is called operator overloading. It allows you to define exactly how an operator behaves when applied to your custom classes. 1. What is operator overloading? It is a specific type of polymorphism where different operators have different implementations depending on their arguments. To achieve this in Python, we use special predefined methods known as magic methods or dunder methods because they start and end with double underscores. 2. Common operator mapping. This table shows how Python maps familiar operators to their corresponding dunder methods. For instance, when you use the plus operator between two objects, Python internally tries to call the double_add__ method. If we implement these methods in our class, we can define our own custom logic for these operations. 3. Implementing custom addition. Let's create a point class representing coordinates. By implementing the double_add__ method, we define that adding 2 points results in a new point object where the x and y values are the sums of the original points. The other parameter refers to the object on the right side of the plus sign. 4. Testing overloaded operators. Now, when we define P1 and P2 and write P1 plus P2, Python automatically calls our custom method. Without this method, Python would throw a type error because it wouldn't know how to add 2-point objects. This makes our custom classes feel like built-in Python types. To summarize, Operator overloading is a high-level feature that provides intuitive interfaces for your classes. You may use this to perform coordinate math, combine bank accounts, or merge data structures. In our final lecture on polymorphism, we will explore runtime polymorphism, where the exact method executed is determined while the program is running. Our next lecture 19.05, Runtime Polymorphism. See you there. Welcome to the final section on polymorphism, runtime polymorphism. Unlike DuckTyping and operator overloading, which are unique to Python, runtime polymorphism is a standard OOP concept found in all object-oriented languages. It relies on inheritance and method overriding to determine which version of a method to execute at the moment the program runs. 1. The mechanism inheritance and overriding. Runtime polymorphism is achieved when a parent class defines a general method, and one or more child classes override that method to provide specific implementations. When a generic reference variable points to a specific child object at runtime, the correct specialized method is executed. 2. Setting up the hierarchy. We define a parent class, shape, with a general calculate_area method. The two child classes, circle and rectangle, both inherit from shape and override this method, providing their own specialized area calculations. The shape method is never intended to be run. It's just a placeholder. 3. The polymorphic function. We create a generic function, print_area, which accepts an object named shape. It calls shape.calculate_area without knowing if shape is a circle or a rectangle. The actual version of the calculate_area method executed is decided at runtime based on the object's actual type. 4. Testing runtime behavior. We call the same generic function with two different objects. When we pass circle, the circle.calculate_area is executed. When we pass rect, the rectangle.calculate_area is executed. The method call is polymorphic because its exact behavior changes based on the object's type, and this choice is made by the Python interpreter during execution. To summarize, runtime polymorphism is essential for building flexible systems where specialized objects share a common interface. This concludes the module on polymorphism. Our next lecture 20.01, Abstract Classes and Interfaces. See you there.